I'm pleased to introduce the speaker for this session, Kumaran Siva. Kumaran is a corporate vice president responsible for the software and systems business development inside the server business unit at AMD, based in Santa Clara, California. In this role, he is responsible for strategic business development and product management of AMD's software and system solutions for AMD Epic processors. Prior to this role, Kumaran managed the cloud business group responsible for the hyperscale business. Kumaran has a broad background in processors and networking, having worked at Inphi, Broadcom, ARM, and PMC Sierra. He has an undergraduate degree in electrical engineering from the University of Waterloo and a master's degree from Harvard University. It will now be our pleasure to hear from Kumaran Siva.
Hi, my name is Kumaran Siva, and I'm from AMD, and it is my honor to be with you today at Rescale's Big Compute conference. Thank you so much for taking the time to watch my video, and I hope this is educational. And I'll hopefully be able to get feedback if you have any other questions or need to get in touch with me. I'm sure there's some link here that you can do that. But anyways, I'll get started. So my talk today is really going to be about the advancement and evolution of CPU technology, especially as it pertains to high-performance computing. So I'm going to give some high-performance computing examples, talk a little bit about what are the careabouts and how the industry fundamentally is evolving, and some of the innovations that AMD have brought that have really, frankly, brought us back into prominence in this area and is driving the industry forward. So first slide. So what is really hindering computing performance and performance gains? Why is this decade not like the several decades prior to it? One key thing is this concept of Moore's law. It isn't so much a law as it is really a statement of where the industry, kind of a goal for the industry, which was that transistors would essentially double in density in a square millimeter of silicon die every, say, 18 to 24 months. If you read through that original paper written by Gordon Moore so many years ago. And that has been true up until probably the last decade or so. And to be fair, it's actually not just doubling of the transistors. What has happened is there's been probably a trifecta, so to speak, of goodness that have come with it. One is, you do double the density and you bring down the size of the die, but that has had a knock-on effect of lower cost. And then also, because these transistors are smaller, and the lower cost comes from simply, if you take the same design and you make it with a newer generation of technology, the die just shrinks, and so the amount of silicon area kind of comes down, right? And so the cost of each transistor is lower to create. It may not be exactly half, but it could be. There was a goodness in terms of the price cost of that transistor coming down. The performance of that transistor went up because the electrons had not as far to go. And then thirdly, because the size of the power dissipation was proportionate to the size of the transistor. As the transistor got smaller, the less power that was dissipated. Unfortunately, as we've gotten deeper into submicron technology, we've reached the point where we see other effects, and then you have to use other techniques, and the power is no longer going down quite as dramatically as it did. The performance isn't going up as much as it did before, and the cost is also no longer going down quite as fast. Now, the cost does come down, and the power performance does get better, and the power does in effect go down, but it's just that rate has dramatically slowed down generation on generation. And then it also takes longer to get from node to node on Moore's law. So one of the strategies that AMD has been looking at, and we've understood this problem for a long time. So we looked at, how do you solve this? By the way, another factor here, and this is that fourth graph in the bottom, is this notion of reticle size. This is the maximum size that you could build a CPU, build a die, right? So it could be GPUs, CPUs, anything, Ethernet switches. The largest you could build a single die. And as it turns out, there's a cap on that. It used to be going up gen on gen, like you could build bigger and bigger die. But because you're building it in smaller and smaller of these submicron nodes, the defects start to overwhelm the die and it starts to fail. And so you're not able to build CPUs as large as you were before. And this has actually been a fundamental limitation to the old traditional design of CPUs. Back in the good old days, you go from generation to generation and, you'd still keep a monolithic CPU. The CPU design would evolve somewhat. You'd be able to add more cores and you'd be able to also get more, higher megahertz performance. And then the cost would also be very much contained. So that has kind of slowed down, and some of it has, frankly, gone out the window. One of our innovations, and frankly, a way that the industry is also moving forward is in utilizing multi-chips to overcome this. So back in 2017, AMD did something. We re-entered back into the server market. We first had re-entered into the desktop and the client arena, but we then re-entered into the server market with our Zen technology, Zen core designs. And the first product was called Naples. It was our 7001 product, and what it consisted of, it was four dies. Each die would have both the memory interface, the I/O interface, as well as the CPUs. So it was a multi-chip design, but it was really putting these down as our first generation, and we learned a lot from it. It actually had a lot of memory bandwidth because each of these dies had memory controllers attached to it, and then they would be able to talk to each other. One of the limitations, though, was that if you were to try to address memory locally, so the memory controllers on the die versus memory controllers on an adjacent or opposite die, the time where the latencies would be different. And this proved challenging for lots of applications. Now, in the HPC arena, we actually saw quite a bit of success because of the memory bandwidth that was brought to bear. Also, we had success in some of the storage applications in the cloud. So fast forward a couple of years later, we brought out our Rome generation. This is our 7002 product. And here we went to a different architecture. We had a central I/O die with CCDs. So this diagram here shows the little big black rectangle in the middle. That is actually our I/O die. And then we have these CCDs, the compute dies that are surrounding it. So we have 4 compute dies and 1 I/O die. That can be up to 8 compute dies and 1 I/O die. And each compute die can have up to 8 x86 really state-of-the-art cores. The compute dies were done in 7 nanometer, and then we leveraged an older Global Foundries node for the actual I/O die. The advantage of doing that was 1, cost. 2, it really aligned the performance to the process node. So I/Os don't benefit as much from gen to gen because you're basically dealing again with physics of sending electrical signals down a wire. So they don't scale as well with process technology. So leveraging the older technology sort of made sense both in economical and from a use case perspective versus the CCDs, the compute die, leveraging the latest and greatest process nodes really bore a lot of fruit and gains for us. Fast forward to 2020 and 2021. So we announced and released the Milan generation of CPUs, which took the same fundamental architecture of having the I/O die plus the CCDs, but really just made the performance a whole lot better, both on the CPU core, the cache hierarchy, the interconnect to memory, the speeds of the DDR interfaces. All of those were upgraded with Milan. And then we introduced a 3D variant of it called the 3D V-cache or Milan, with Milan X. So it's became the X line of products for our CPUs. And this is the first mainstream CPU that actually has stacked die technology. These stacked dies can be either memory or they can be logic. It can be accelerators. They can be more CPUs. What we chose to do in this first generation is actually put down an additional SRAM. And we'll talk about the details on that in a couple of slides. But the net effect of it was that you're able to now leverage this to go address new and better applications and make it, continue that Moore's Law, the gains that one used to expect generation to generation by introducing literally a new dimension, in which we could innovate on. Really also equally important, in the design of our CPUs, and this really goes to the heart of the design, not just the architecture with the chiplets, but also the design of the CPUs themselves. We've been very, very focused on power consumption. So one of the things that I think, in the past, it's been all about how do you get bigger and better CPUs, and power consumption was a secondary concern. What has really transformed over the last few years is power per watt is now becoming super, super important. And so while, if you're using Uniscale, you're using the cloud, and maybe it isn't as much manifested as your problem, but you are saving the earth by using AMD, and it also shows up in your bill because the power consumption, the power efficiency of the AMD CPU is so good. So what we're showing here is the example from Frontier. So Department of Energy has obviously a series of supercomputing computers that they put out every year. They'll have a different supercomputer, a different supercomputer center. One of the prior generation systems was called Titan, and between Titan and Frontier, which is the latest generation supercomputer powered by AMD CPUs and GPUs, we actually see about a 430 times power reduction. And this was necessary to hit the performance point that the DOE wanted, which was an exaflop. Now, they basically modeled their power consumption around about $1 million per megawatt of power per year. If they were to have built an exaflop system out of the Titan components, we would have ended up with about a $3 billion a year power consumption. So you can tell that was just completely impractical. So they really set a target, not just for performance of exaflop, it has to be a performance per watt. A lot of that innovation that came in the AMD CPU was the focus of not just taking advantage of eking out the gain that they could get from the process node, but actually making the CPUs themselves optimized for performance per watt. Using a variety of techniques, but keeping that top of mind. So deep dive or kind of a deeper view into the actual, the third generation is the 7003 family of Milan CPUs. Again, memory I/O die that has on the top connections to potentially other CPUs to be able to put together a 2P kind of configuration. On the bottom side, we have connections to I/Os. So it shows you the PCIe Gen 4 connectivity. On the sides, we have the DDR connectivity and also the I/O die, the CCD, the compute. These are what we call the CCDs. These consist of 8 of the Zen 3, up to 8 of the Zen 3 cores. You can have fewer, of course, but that has a L2 caches associated with each core, and then a shared L3 cache. So within the CCD, if you have optimal code design, you can actually take advantage of really fast sharing between those Zen 3 cores. Now, with the 3D stacking technology, you're able to take an SRAM, put it on top of this Milan CCD, and get up to 96 megabytes per CCD of L3 cache that's again shared. Now, really cool examples here are really cool workloads that have been used here. We've had customers take large AI models and split them up into 96 megabyte chunks, be able to run that whole model on the L3 cache. So a lot of very tight memory management in that use case, but man, amazing results in terms of being able to get really high performance inference applications and use cases. Stuff that works really well out of the box. We have seen database applications that are very cache sensitive be able to utilize this, giving us even better. We've had world record results with TPC. We've been able to show that in various benchmarks even better with the 3D cache. And then, of course, HPC applications, in particular, computational fluid dynamics, finite element analysis, and then also electronic design automation. In fact, all of our new chips are actually designed using Milan-X, EDA running on Milan-X systems, which gives us better time to simulation and helps increase our engineers' productivity, which is really fundamentally the value proposition we bring here with AMD. So with and without the 3D kit, 3D stacking, we have the best large caches with high performance CPUs, world record performance across a variety of workloads. You get workloads that are single-threaded that need these Zen cores to run as fast as possible, and they do have very high boost frequencies. And we have configurations where you have fewer cores per CCD, and so you have more cache, and each core can run at a higher frequency, higher base frequency or higher average frequency, and then boost up to the theoretical minute maximum there. And then we have throughput applications where you have all 8 CCDs with 8 Zen 4 cores, 64 cores, and that screams through really well through throughput related applications. So on that line, and in the interest of also kind of maintaining the baseline technology for HPC, we're introducing the Genoa CPU, in a few days actually from when this presentation is shown. What we'll talk about there is give you more details, but really at a high level, we're taking what was 64 cores top of stack, so the highest part we produce, and driving that up to 96 cores, and introducing the Zen 4 core design. This was also announced in our Ryzen CPU products a few months ago, and now it's in the server form. 5 nanometer design, extremely high instructions per cycle, large cache, so extraordinarily capable. It's going to be available in a number of the cloud providers and also in OEM. So it'll be available for consumption through Rescale, at some point. It also has 12 DDR5 interfaces. So this provides you with, leadership, memory bandwidth capacity, and then also goes to PCIe Gen 5. It also integrates CXL, and CXL.mem is an area that we have focused on. And what that allows you to do is gives you the ability to have memory expansion associated with the CPU. So it's no longer just about memory that's attached directly. You could have sort of NUMA memory because the latency is different, but have memory attached through CXL as well. So lots and lots of memory bandwidth with lots of cores and lots of high performance. So super exciting product. The other area that we have focused on is confidential compute. And so we pioneered memory encryption technology. So being able to, kind of transparently encrypt both you have encryption encryption at rest. You have encryption in transit through networking, and then now you have encryption in compute through the memory that's attached directly to the CPU. And the technology is advanced. In the Milan generation, we were able to have not just memory encryption across the entire DIMM or the entire memory, but also on a per VM basis, so you could have multiple tenants. that were encrypted, and protection from the hypervisor. We have a number of white papers that describe the capabilities that are there. We're now extend that capability to CXL as well. So this is very powerful from that standpoint. Now, bringing it back up to an application, and why do you care, and what does this all mean to you? So first off, if you think about kind of applications, and this slide really talk about computer-aided design, manufacturing type applications that we typically see in the commercial HPC space. Baseline, we are very compatible, right? AMD created the 64-bit x86 ISA that's in all of the x86 processors, including AMD and Intel. And so we have pioneered that piece of it. We've been a big part of the history of x86, and so we have very good, strong compatibility across the board. Almost every application that I've seen, majority of which you just plop on an AMD processor and it just works well without even doing any optimizations. And then you can do a little bit of tuning to get even more performance. And for those that really want to go take advantage of very large caches, for example, and there are a number of HPC customers that do that, you get even bigger benefits. So there's lots of capability, but lots of support for existing code. On top of that, really what I've heard about probably more in the last few months, especially this year, given all the global events that's going on, energy consumption, power costs top of mind for pretty much every enterprise out there. And also there's sustainability goals that people even put onto their cloud vendors, and we work with cloud vendors to be able to give them the best power performance, and so it's really important, even through Rescale, that you use AMD technology, and so that being as we talked about the focus there, that has become a key value proposition for us, and we have a very strong story around the sustainability results of using AMD infrastructure. Then there's really there's a set of use cases, but I really look at it as two major buckets of use cases that really benefit from the AMD architecture. Ones that need compute power, both single-threaded and throughput performance, we lead. And so in a lot of the applications that need one extreme or the other, we do extraordinarily well. The other side of it is applications that need lots of memory bandwidth. So as I mentioned, with the Milan generation, we have 8 DDR4 channels, and then with Genoa generation coming out in a matter of days, that goes up to 12 with DDR5. So it's tremendous amounts of memory bandwidth that feed those cores that allow applications to run extraordinarily efficiently within a node. So to summarize, so bringing back to kind of where AMD fits into this, and part of how we see continuing to drive CPU technology. One key thing that AMD has done, in partnering with foundry partners like TSMC, we've been able to deliver the product on time, on schedule, and so this has given us, kept what advantages you can still get from that, Moore's law, node on node, kind of gains. We've gotten that, and we're able to translate that into value for our customers, both in the cloud and on premises. We have, extremely powerful CPU cores, and we continue generation on generation to extend the capabilities of those CPU cores and to increase the performance with a particular eye on performance per watt. Right, so it's not just performance for the sake of performance. It is performance at the the best possible performance at the looking for that when you do the design, trying to find that optimal point of here's where you get the best amount of performance for the amount of power you get. And if you go further up, you still get more performance, but it gets it starts to the returns start to diminish. In an unacceptable way. So we aim for that kind of design point as we build this. Another key feature of AMD, now AMD is really started to aggressively invest in the software ecosystem, both outside of AMD and then also inside of AMD in terms of library development, compiler development, but also going out and enabling a number of these HPC applications that Rescale can then leverage and utilize, in the cloud and make it easy and performant for you for end customers to get on board and to be able to utilize those. Just in general, driving innovation and being able to deliver, finding ways to deliver generation on generation improvement that you've come to expect. And so AMD sort of picked up that mantle, and we've been driving that fairly hard. So that's the end of my presentation. I hope you've enjoyed listening to me and to learning a little bit about CPU technologies and some of the challenges here. Thank you very much.